Electronics Lab Kit, Concept and Prototype by Dave Smith. In many electronics classes, there is a need to build and test various circuits. Having a personal lab kit in which circuits can be constructed, measured, and saved for later use without the need for disassembling and reassembling would be a great time saver in completing labs. The kit should include a built-in power supply with both positive and negative voltage terminals, a breadboard area large enough to hold multiple circuits, and a storage compartment for components, wires, and tools. In the text, Electronic Project Design and Fabrication, on page 354, you will find the schematic for a dual voltage power supply. This is a proven design, but it lacks a 5-volt supply that is needed for some of our transistor logic lab experiments. The revised diagram below has an additional fixed 5-volt circuit incorporated into the schematic. An old DeWalt drill case proved to be large enough to house the power supply, breadboards, and provide ample room for storage. A custom cover plate will be fabricated to enclose the power supply, and a cutout will be made in one end of the case for a power cord receptacle. Using the schematic previously shown, a working prototype was built on the breadboard. This led to the discovery that the schematic given in the textbook has some of the capacitors reversed. Further research into power supply design also led to the discovery that the LM series of power regulators require a minimum load on them to function properly. To put a minimum load on the power regulators, indicator LEDs were added to the schematic. Autodesk Inventor was used to lay out the overall design and to formulate the basic size, shape, and placement of the components. After creating a working schematic in Multisim, the design was transferred to National Instruments Utiliboard, where the component placement and circuit board traces were finalized. After having the circuit board milled, it was necessary to enlarge a number of holes for a terminal block and the heat sinks. In the image on the bottom, you can see the importance of having good component data. The pin location specified in the Utiliboard model did not match the actual part. This was corrected by drilling new holes that matched the terminal block pin spacing. The original assembly made use of high-power LEDs. It was later discovered that when the potentiometers were set to about 1/3 power output, the LEDs would turn off. By replacing them with low-power LEDs, they remained lit for the full swing of the potentiometer. Another obstacle in this build was that the through holes for the diode were placed directly under one of the heat sinks. This was an easy mistake, as Utiliboard did not have the correct heat sink model for this assembly, and a guess was made for where the components needed to be placed. The top right photo shows the new location for the homeless diode. The correction was made by drilling new holes in the current trace lines. After assembling the various power supply components in the case, testing was done to ensure that all was working as it should be. It was discovered that the negative voltage side of the circuit fluctuated wildly, while both the positive voltage and fixed 5-volt circuits were quite stable. By slightly flexing the board, the negative voltage output could be made to remain stable. This is a good indication that there were bad solder connections. By reheating and adding a little more solder to the joints, the negative voltage supply was made stable. In all, this was a very educational project. I have a new appreciation for circuit board manufacturers and the obstacles they must overcome. While fabricating the circuit board, I discovered a few mistakes in my design, but was able to modify the board to create a working product. Don't assume the design you are given is correct. Careful study and further research should always be a part of any design manufacturing process.